Okay, hello everybody. This is a Zoom meeting for the examples in chapter 6. Example problems, chapter 6. And we're going to start obviously on 6.1, which states, Steve exerts a steady force of 200 newtons on a stalled car as he pushes at a distance of 8 meters. The car also has a flat tire, so to make the car track straight, Steve must push at an angle of 30 degrees to the direction of motion. How much work does Steve do? And B, that's A, how much work does he do? B, in his helpful mood, Steve pushes a second stalled car. Steve is a mensch with a force of 160 newtons I minus 40 newton J. The displacement of the car is S equals 4 meters I plus 11 meters J. How much work does Steve do in this case? All right. All right, part A. From work equals force, distance, cosine theta. So what do we have here? We've got work equals 210 newtons. And we have 18 meters times cos, is that 30? 30. And that is going to equal 3.3 times 10 to the third joules. Okay, part B. From work equals F dot S. And we've got that equals F of X times X plus F of Y times Y. F of Y of Y. All right, so we have, what was his deal here? F equals 160 newtons I minus 40 newtons J. And then S equals 14 meters I plus 11 meters J. Okay, so we'll go ahead and do our operation here. Equals 160 newtons times 14 meters plus a negative 40 newtons times 11 meters. And we're going to get 1.8 times 10 to the third joules. 10 to the third joules. 6.2 is work done by several forces. And it says a farmer hitches her tractor to a sled loaded with firewood and pulls at a distance of 20 meters along level ground. Okay, so delta X equals 20 meters. And let's see, the total weight of the sled and load. So weight equals 1470 newtons. 1470 newtons. The tractor exerts a constant 5,000 friction force, 5,000 newtons, at an angle of 36.9 degrees. Okay, above the horizontal. Oh, okay, so the tractor's got some kind of chain to it. A 3,500 Newton friction force opposes the sled's motion. We have another, this is one. 3,500 Newton opposes the sled's motion. Find the work done by each force acting on the sled and the total work done by all the forces. All right, so the work done by the weight is 0 because that is perpendicular to the direction of motion. So work of weight equals 0. All right, we are on problem 6.2. And 6.2 says, got to sit more upright. Says, a farmer hitches her tractor to a sled loaded with firewood and pulls it a distance of 20 meters. Delta X equals 20 meters. A low level ground. The total weight of the sled and load is 14,700 newtons. So weight equals 14,700 newtons. The tractor exerts a constant 5,000 Newton force. So force of the tractor is 5,000 newtons at an angle of 36.9 degrees above the horizontal. Theta equals 36.9 degrees above the horizontal. A 3,500 Newton friction force opposes the sled's motion. Equals 3,500 newtons. Find the work done by each force acting on the sled and the total work done by all the forces. Okay, so the work done by gravity is going to be 0 because that is perpendicular to the direction of motion, and the cosine of 90 is 0. So that's 0 as well as the work done by the normal force. Okay, and what we've got some kind of deal that looks like this. You got this guy, and let's see, this, the track, and this is the tractor. And it's just pulling that. And so this angle right here is 36.9. All right. So now the work done by the tractor, WT, is going to equal FS cos theta. All right. That's magnitude F. Okay, anyway, let's see. It's going to be 5,000 newtons times 20 meters times cos 36.9. And that's going to work out to, let me just get their answer, 80 kilojoules. And the work done by the friction on the sled, now it always opposes the direction of motion, so it's that way. So that's going to be work by friction equals 3,500 newtons times 20 meters times cos 180, right? 180. And that's going to be negative 70 kilojoules. So the work total equals the work from the weight plus the work from the normal force plus the work from the tractor plus the work from friction. And that equals 0 plus 0 plus 80 kilojoules, 80 kilojoules, minus 70 kilojoules. And our total work here is going to be 10 kilojoules. All right. In example 6.3, we are using work and energy to calculate speed. Oh, up there. Okay, so let's see. And it says, let's look again at the sled in figure 6.7 and our results from example 6.2. Suppose the sled's initial speed is 2 meters per second. So VI equals 2.0 meters per second. What is the speed of the sled after it moves 20 meters? So we want to know VF at 20 meters, or at the end of our problem there. Remember, recall that we solved for a displacement of 20 meters. All right, so I'm going to use the work-energy theorem, which says, and we've got a constant force here, so I'm going to do work total equals K final minus K initial. So yeah, or delta K. And we've defined K equals 1/2 mv squared. So I'm going to do work total, which was 10 kilojoules, right? 10 kJ equals 1/2 m, and then v final squared minus v initial squared. All right. So I need m. And let's see, what was that weight of the tractor? 14,700 newtons. So I know weight equals mg. So m equals weight over g. So m is going to equal 14,700 newtons divided by 9.8 meters per second squared. And let's see, just to be real quick, your book gives me a value of where is that? 1,500 kilograms. So 1,500 kg. Now I'm gonna pause and clean off my board and I'll be right back with you. All right, so we've got 10 kilojoules, or 10 times 10 to the third joules equals 1/2, and my V, I'm trying to find my V final, yeah, times 1,500 kilograms times V final squared minus 1/2 times 1,500 kilograms times V initial squared. And let's see, let me just get their values. They use, let's see, V final. Let's see, they got kinetic initial is 3,000. This is 3,000 right here. This is 2 squared. That's 3,000. And I don't know what this is, but I know that this whole total, 10,000 joules equals this K final minus that. So K final's got to equal 13,000 joules. All right, so here we are with K final equaling 13,000 joules. Now I've got to solve for V. I'm going to pause, erase the board, and be right back. Okay, let's see. I knew that my final kinetic energy was 13,000 joules. And let me erase this guy. I know what M is. All right, so I equated that to my equation. Kinetic energy equals 1/2 mv squared. I know my m is 1,500 kilograms, so I multiplied both sides by 2, divided both sides by 1,500 kilograms, took the square root of both sides, and got 4.2 meters per second for my velocity. 6.4 is forces on a hammerhead. And this is a big hammerhead. All right, it says a 200 kilogram steel hammerhead. 200 kg. I don't know what the significance of steel is, but strong. Of a pile driver is lifted 3 meters above the top of a vertical I-beam. So delta X equals 3 meters, 3.00 meters. The hammerhead is then dropped, driving the I-beam 7.4 centimeters deeper into the ground. So the delta X of the hammerhead, delta X of the I-beam equals let's just 7.4 centimeters. Let's go ahead and convert that. 0.074 meters into the ground, right? Let's see. The vertical guide rails exert a constant 60 Newton friction force. So force of friction equals 60 newtons. Well, I guess they're kind of making sure the hammerhead doesn't go off in one direction or the other and stays pointed vertically down. So they're rubbing against it. Use the work-energy theorem to find A, the speed of the hammerhead just as it hits the I-beam, and the average force the hammerhead exerts on the I-beam. Ignore air resistance. All right, we're going to talk about as the hammerhead is falling before it hits the I-beam. All right, as it's falling, we've got the force Fg minus the Ff, and that's the net force, and then times delta X is going to give me my work, change in work. So I don't know what this thing weighs. Let's see. It weighs 200 kilograms. So my work is going to be 200 kg times 9.8 meters per second squared. Oh, and this is like this, you guys. All right, and that's minus, what is friction? 660 newtons times 3 meters. That equals my change in kinetic energy. It equals work. And that value, let's see. Let's see if I can get that up real quick. On clear. 200 times 9.8 equals minus 60 equals times 3 equals. Okay. I'm getting, let's see, 5520. Okay, 5520 joules. Your book is getting a different value. Did I use everything right here? Let's see. 1900 newtons. Did they round? 1960. Let's see. 200 kilograms times 9.8. Let me make sure I did this right. We're 2000 times 9.8 equals minus 60 equals times 3 equals. Okay, now I do get that same value. A little arithmetic error there. Okay. So my delta EK is 5,700 joules, and that's going to equal to 1/2 mv squared. And I know my initial velocity is 0, so it's just going to equal to 1/2 mv final squared. I'm assuming it starts from a dead rest, right? Okay, so let's see. I have 5,700 joules equals 1/2 times 200 kilograms times v squared. And so let's see, 5700 joules times 2 divided by 200 kg under the radical is going to equal v. And hopefully I can just pop this answer from them. They give me 7.55 meters per second. So that velocity of that hammerhead, V of hammerhead, right before it hits the I-beam, is 7.55 meters per second. Okay, very good. Pause, clear my screen, and continue. Okay, now I need to calculate the average force the hammer exerts on the I-beam. Okay, so we still have the friction. Let's see, I needed that force that I probably just erased. I got my total work was, I didn't get that. Oh yeah, five. Okay, my total work is 5,700 joules there. Okay, and I know that since I started from rest, this is going to be my equivalent to my final kinetic energy. And I'm going to end at rest. So this is going to be my change in kinetic energy. So once again, I've got this 5,700 joules equals my force, F, times a distance. And what am I calculating here? Let's see. Okay, now this time, I've got a normal force from that I-beam operating back on my hammer. So I'm going to have my force acting on it is going to be equal to the weight of the hammerhead minus the friction and minus that normal force. And that's going to be times D. And that's going to equal to my change in delta K, which is, I come in at 5,700 joules. I go to a dead stop, so it's going to be 5,700 joules. So let's see, for my weight, I've got 19,600 newtons minus friction, 60 newtons. Minus my normal force times that little distance. What was that? 0.074 is 0.074 meters equals delta K, which was 5,700 joules. So this is the value I want. So we'll do 19,600 newtons minus 60 newtons minus N equals 5,700 joules divided by 0.074 meters. So now I'm going to get N equals 5,700 joules divided by 0.074 meters. That's minus 1960 newtons plus 60 newtons. And I'm going to get 79,000 newtons. Oh, and that's going to be minus N. So this is going to be plus 79,000. .5 is comparing kinetic energies. It says two ice boats, like the one in example 5.6. Section 5.2, hold a race on a frictionless horizontal lake. The two ice boats have masses m and 2m. So we're dealing with an m here and a 2m. Ice boats have identical sails, so the wind exerts the same constant force F on each ice boat. They start from rest and cross the finish line a distance s away. What ice boat crosses the finish line with a greater kinetic energy? Okay, so if we have F cross D and we have the same force and the same distance, I'm going to say they're the same. But let's see what your book says. They are the same. They've got to be the same. Force F D cos theta, they're going straight, equals delta EK, work-energy theorem, that's work. And we got the same force, we got the same distance, the same angle. It's going to be the same, everybody. All right, this is example 6.6. It's done on a spring scale, and it reads, a woman weighing 600 newtons steps on a bathroom scale that contains a stiff spring. In equilibrium, the spring is compressed 1 centimeter under her weight. Find the force constant of the spring and the total work done on it during compression. Okay, so the force constant, F equals Kx, and that's the force constant of a spring, and X is the amount of displacement. So what's going on here? We put 600 newtons on the spring, and that's K, and we displaced it a distance of 1 centimeter, which is boom, boom, 0.01 meter. So K is, this is 600 newtons divided by 10 to the negative 2. That's going to be 60000 newtons per meter. And note that this guy, this is the unit, and that means this is the stiffness, basically the stiffness of a spring. So that means every meter that I displace this spring from its equilibrium position, I'm going to have to input 60,000 newtons. So this is a pretty stiff spring. Okay, now I'm determining the total work I've done on the spring. So in a spring, I've got to work, we got a varying force. So work equals, well, you can do the integral. It's from x1 to x2 f dx. So that's going to give you 1/2. F is kx, remember? K. So I'm going to go call this, let's just do it properly. Let me erase. This is going to equal the integral of K, and then F is Kx, x dx from x1 to x2. I've just redefined K here. So this is going to equal to the change in work, or the total work done is going to equal 1/2 kx squared. So there you go. So that's what we're going to do to find this. So we've got, we're trying to find the work. So we've got x final squared minus 1/2 kx initial squared. All right, but we know we were at the equilibrium position before the lady steps on the scale. So this is what's germane. So we've got 1/2, and that's 60,000 newtons per meter, times 0.01 meters, quantity squared. Hopefully your book has that value for me. Is 3 joules. 3.0 joules. That's the answer. And this was example 6.6. Example 6.7 is called motion with a varying force. And it reads, an air trap glider of mass 0.100 kilograms. So mass equals 0.100 kg. Is attached to the end of a horizontal air track by a spring with a force constant of 20 newtons per meter. So K equals 20 newtons per meter. Initially, the spring is unstretched and the glider is moving at 150 meters per second. No, 1.50. V equals 1.50 meters per second to the right. So we're going to call that positive, I guess. Yeah. Find the maximum distance D that the glider moves to the right. A, if the air track is turned on, so there's no friction. And B, if the air track is turned off so that there is kinetic coefficient. UK is 0.47. UK equals 0.47. All right. All right, from my work-energy theorem, I know that the work done is equal to the change in kinetic energy. It's also equal to the change in elastic potential energy. So I'm going to equate those kinetic energies to that elastic potential energy. So we've got a elastic potential is negative 1/2 kx squared equals 1/2 mv squared. I don't need these halves. And so I'm going to get, let's see, a little correction. I've got a negative 1/2 kx squared equals the change in kinetic energy, and that's 0 is going to be the final, minus 1/2 mv squared. So yeah. Okay, so I can take these off and I can take these off and I'll be happier. So now we've got kx squared equals mv squared. And what am I solving for? I'm solving for x, right? So x squared equals v squared m over k. And I'll take the square root of all those. And I'll get, oops, away. There. I'll get x equals v square root of m over k. And now let me pause, clean up the board, fill in the blanks, and we'll. All right, I'm going to resume my calculations. I've got x equals 1.50 meters per second times the square root of k was 20 newtons per meter divided by the mass, which was 0.100 kgs. And wait, am I right? Yeah. Oh no, I've got this wrong. It's m over k, yeah. Okay, it's m over k, right? So it's 0.100 kgs divided by how many newtons per meter? 20 newtons per meter, 20 newtons over meter. And that's going to give me a distance of 0.106 meters. X equals 0.106 meters. And that's the first part. Okay, so now we had the work done by the spring on the glider and the work done by friction are going to equal to the change in kinetic energy. So the work done by the spring on the glider is -1/2 kx squared. And the work done by friction is going to be minus mg mu k. And that's going to equal to the change in kinetic energy. And we have coming to rest -1/2 mv squared. So let's go ahead and do this. -1/2. What are we solving for again on this one? We're solving for v. We are solving for, let's see. Okay, v, right. We're solving for, no, we're solving for d again, distance, yeah. All right. So here we go. So let's see, I'm solving for this value right here. So I've got -1/2 kx squared equals -1/2 mv squared plus mg mu k. And let's see, well, I have to do all this algebra? Wow. Let's see, I do, don't I? That's a lot. Okay, where did the 2 go? Let's see, let me just pause a minute and look. Okay, I forgot an x right here. Friction is, the work done by friction's got to have a distance. All right, so going forward with this, I get 1/2 kx squared minus mg mu kx plus 1/2 mv squared, and I'm going to equal to 0. And now it's a quadratic formula, and we have to do that. Okay, let me clear off some space. Okay, so now I rearranged my equation to this. And now it's we have the displacement as our variable. It's a quadratic formula. I filled it out here. Let's see, this was a 0. Let me just do 0.47. Amen. Right here, 0.47. So this is my A variable. A, this guy is B, and this whole thing is C. And I would do that quadratic formula, but I gonna just go with the book's answers. And the book gives me x1 equals 0.86 meters and x2 is negative 1.32 meters. And since the glider has a positive displacement, we're gonna go with this guy. But if you want practice with the quadratic formula, this is A, that's B, and that's C. Very good.